All right, guys, today we're going to talk about chapter 4. All right, so let me pull up chapter 4 and see if we can't get this thing running. All right, so let me open up my pen. Oh. Corner options pen. All right. So in this PowerPoint, we're going to be talking about aqueous solutions and reactions that occur there. So aqueous solution, when we're looking at a reaction, it's going to show up as that little AQ at the bottom of a reactant. So some things that we did last year that are going to come into play here. Predicting reactions, okay, especially our single and double displacement reactions. We're going to look at a new couple kinds of reactions and how to predict those. We're going to look at electrolytes and non-electrolytes, and then we'll probably take a break. Okay, so let's just start with a little review. A solution. A solution is a mixture that is homogeneous, right? It looks the same throughout. It's uniform. And whenever you have those mixtures, you have a solvent, which is doing the dissolving. You have a solute, which is the thing getting dissolved. And last year we learned that, hey, if you see AQ in a reaction, that means that water is doing the dissolving. So if I want to, mix hydrochloric acid with something, it's not pure hydrochloric acid. It's hydrochloric acid dissolved in water, and I'm doing aqueous chemistry. I'm doing chemistry that is suspended in that water surface, right? That's our platform for our reaction. And in first year chem, we pretty much stop there. We don't really go much further than that. Here in AP, we're going to go a step further, right? We're going to grow on it. So something to think about with aqueous solutions. Sometimes when you put things in water, they dissolve. Sometimes they dissolve and split into ions. Sometimes they dissolve, split, and then react with the water. So we want to kind of understand that process. So let's look at just dissociation, right? If you put an ionic compound into solution and it dissolves into the water and it breaks apart into its ions, then that is called dissociation. And you can see right here, right, an example of how something dissociates. This is our hydration shell. Okay, and remember that water is a polar molecule. Okay, it's got a partial positive and a partial negative charge. It has a dipole moment, moving towards oxygen. This is our negative end. And so if I have just some ion, the positive end is going to naturally be attracted to the oxygen end of water. And on some ion with a negative charge, it's going to naturally be attracted to the hydrogen end of water. And so water can surround the ions in a hydration shell, right? It's surrounded by water, it's hydrated, and it will break them apart into their ions. And we did look at that in first year chem, so hopefully that's familiar. Now, something that we didn't really talk about is the fact that molecular compounds, they will interact with water, they can dissolve in water, but they don't dissociate. So like here in this picture, we can see that methanol is surrounded by water. It's not quite the same as the hydration shell. It's not that, electrostatic attraction per se, but it is still, caged in by those water molecules. Finally, just as a subset, and this is not something that we really look at a whole lot in AP, but sometimes when you put a molecular substance into water and they dissolve, they actually will react with the water. So that can be exciting, all right, when you're not expecting that to happen. But for the most part, we're looking at the first two bullet points as we move forward. So the next thing we're going to look at is, once you have dissociation, how does this change the behavior of that solution? And in order to describe that, we use the term electrolyte and non-electrolyte. So electrolytes, when they dissociate in water, they are moved into their ionic state, their ionic form. So salt, like table salt, is a good example of this. When you put it into, a beaker of water, right, you get Na plus and Cl minus. And they are completely surrounded by those water molecules. okay, and they are, stable in that ionic form. A non-electrolyte can dissolve in water, but it's not going to dissociate. So methanol, right, would be a good example of that. Now this table right here, these are some good facts to know. First, your ionic compounds are generally considered to all be strong electrolytes. If they dissociate, they're going to be stable that way. Now, not every ionic compound dissociates, right? A good example of that would be PbI2, which we'll see in a moment. This is obviously a metal, right? Lead and a non-metal. So it's definitely an ionic compound. But when you put it into water, it's actually a solid. It's a beautiful yellow solid, okay? So if they dissociate, then they are all strong electrolytes, okay? There's no such thing as a weak ionic electrolyte or a non-ionic electrolyte. Molecular compounds are a little bit more complicated. And remember, the difference in ionic and molecular compounds comes, one way we can figure that out is the Pauling scale, right? So we look at the difference in electronegativity from the two molecules. And a strong acid, our strong acids like HCl and HBr, I think nitric acid, sulfuric acid, those are molecular acids, but they also, when they go into water, dissociate. Even though they're molecular compounds, they dissociate and are stable in that ionic form, and they form a strong electrolyte. So sulfuric acid is one of those. This is what sulfuric acid looks like. So I can draw that there. And when you put it into water, one of the hydrogens pops off and you get O minus. Like so. And actually, we'll talk about this later, but sulfuric acid is a diprotic acid. You can actually also take that hydrogen off. It's just a little bit more difficult. But anyway, that's an electrolyte and a non-electrolyte. Here's how you test for them. Here's the easiest way in the world to test for them. This would be a phenomenal, like, middle school lab experiment. This would be a phenomenal AP lab experiment, depending on the depth you went into with your analysis. But basically, you take a battery, right, just like this. You need a light bulb. So I'll see if I can draw a light bulb here. Right. Got a filament in there, all that good stuff. Yep. And we have a container with solution. We run an electrode into that solution. We run another electrode straight to the battery, and we connect our circuit. So I know the battery is off screen here, so I like to show that. All right. Anyway, pure water is...
Attention all teachers, If you have additional items that need to get to students, please bring them to the main office. Do not take them to the gym. There are no books in the gym any longer. Please do not take items to the gym. Just bring them to the main office. Thank you.
All right, so if you need to pick up something, it'll be in the main office. I don't know if you guys could hear that announcement. Anyway, so I like to show the battery just so you guys see what's going on there. If I want to test whether or not something is a strong or a weak electrolyte, once I have water, because pure water does not conduct electricity like at all, I can see that my light bulb here is not lit up, and I add the solid, the ionic compound or the molecular compound, whatever it is. If the light bulb does not light up, well, then it's a non-electrolyte. If it lights up strongly, then we're going to say it's likely a strong electrolyte. If it's very weak or it flickers, it's probably a weak electrolyte. And based on the intensity of the light, we can kind of determine, hey, is it a strong electrolyte? Is it a weak electrolyte? And that would be an experimental way for us to define our electrolytes. There are, however, some ways that we can, theorize or rules that help us determine whether or not something is going to behave as an electrolyte. So how you kind of want to think about this in your mind. A strong electrolyte has to completely dissociate. If it completely dissociates, it is soluble in water, okay? So solubility and status as an electrolyte are married by the behavior of those molecules, right? The dissociation of the molecule, right, connects solubility and electrolyte behavior. So you need to memorize this set of rules. We want to memorize it. Memorize these rules. Now, they're not overly complicated because you can see, like, there are some pretty common sets of rules, like, this rule and this rule. The exceptions are the same, okay? Let me see if I can open something here. Eraser. All right, so let me get rid of these little dots for a moment. Okay, anyway, let me get my pen back. Okay, so how do we use this? Why do we want to memorize it? All right, well, here we go. So last year, I give you an equation, something like, let's say this, HCl plus Mg. And I would say, all right, magnesium plus hydrochloric acid. I want you to predict the reactant. And you guys learned, hey, this is a single replacement reaction. I have a metal by itself. I have hydrogen out front, which means it's acting like a metal. And I have a non-metal here. So this is an ionic compound, or, well, not an ionic compound, sorry. This is a compound that has a metal and a non-metal involved in it. And so we learned last year, hey, spot this. This is single replacement. I should get hydrogen by itself and magnesium with chlorine together. Well, we know that hydrogen is one of the diatomic molecules, right? We memorized that last year, so we know it's H2. I know that magnesium is a +2 ion. I know that chlorine is a -1 ion. So I'm going to cross the charges, drop the signs. So I'm going to get MgCl2. And then I know, okay, we need to balance that. So 2 chlorines, that gives me 2 hydrogens, 1 magnesium. So everything else is a 1. And last year, that was all we needed to do with predicting reactions. That's a good skill to have. I mean, you still need to have that skill. But we want to take it a step further. We want to be able to add aqueous, liquid, solid, gas. We want to be able to add these little monikers to further describe our reaction. So hydrochloric acid is a strong acid. We learned that last year. We just saw on the last slide that strong acids are soluble. They're strong electrolytes. So that tells me it's aqueous. I also have chlorine here. And you can see that chlorine is a soluble ionic compound, or is going to be soluble when it's ionic, unless it's with silver, mercury, or lead. So even though I know this is a molecular compound, because it's dissociating, it's acting like an ionic compound. So that also lends some light on our problem and says, yeah, this is probably aqueous. Magnesium is a metal. It's on the left side of the periodic table. It's in group 2. It's an alkaline earth metal, and I know that metals, with the exception of hydrogen, are solids at room temperature. Hydrogen is a gas. We know that hydrogen is a gas at room temperature. And then we have magnesium chloride. And this is the one where the rules become really important. So I'm still looking at chlorine, okay? And chlorine, when it's an ionic compound, is soluble unless it's bound to silver, mercury, or lead. Well, it's not bound to silver, mercury, or lead. It's bound to magnesium. So I know that this is going to be aqueous. And that's important. This reaction is not going to have a precipitant. However, I know it's going to produce gas. I know that gas is flammable. Okay, we know that hydrogen is a flammable substance. So I know that if I take magnesium metal and I put it in hydrochloric acid, that I'm going to create a flammable gas and a solution of magnesium chloride. And I would expect that solution of magnesium chloride to conduct electricity, right? This is a strong electrolyte. That's what we want to be able to do. We want to be able to describe a reaction in great detail, right? Just by looking at it and, looking at the reactants. So we started with just acid and a metal, and we have now said we're making a gas. It's flammable, so we need to be careful around it. No open flames. We have an ionic solution left behind. that should conduct electricity. We know it's not going to be a precipitation reaction. Okay, these are good things to be able to identify about a reaction. If you don't memorize the list, you're not going to be able to do that. So make sure you memorize the list. Let's look at precipitation, because if that set of rules tells us that something is not going to dissolve, which in this case is exactly what's going to happen, then we know we have a precipitant, and we can predict what the precipitant is going to be before we ever do the reaction. So here we're going to write out, let's write out the reactants on the left. We have potassium iodide, and we have lead nitrate. And then we're going to do our reaction. So there's the big arrow. And we're going to make potassium nitrate and PbI2, lead 2 iodide. Now, back to my rules, right? We've memorized our rules. We know that nitrates are always soluble. Nitrates have no exceptions, so they are soluble. So I know that anything that has nitrate on it is going to be aqueous. So I can add that descriptor. I have potassium iodide. All right, that's a metal and a nonmetal. It's definitely ionic. So I know that some of my halogens have exceptions, right? These are all halogens. Okay, let me grab my eraser so I can get rid of some of this extra stuff. That way I can highlight it again. Yeah, some of my halogens have exceptions, right? These are the exceptions. But potassium, K, right, is not one of the exceptions. So iodine must be soluble unless it's with silver, mercury, or lead. Now look over here on the right. Well, I have iodine. I know it has exceptions. I know one of those exceptions is Pb+2. So I need to know, is this lead, when it's an ion, Pb+2? All right, well, let's look. I have I2 and I have Pb. So I know I'm going to uncross the charges, 1, -1. And I ask myself, hey, is that the normal charge for iodine? Yes, it is. So that must be the charge on lead. So I have Pb+2, and this is a solubility exception by rule. Right. What I'm saying is when iodine is bound with Pb+2, it is an exception to the solubility thing. So exception equals not soluble. So this must be a solid. And that's how I can look at this reaction and say, oh, I'm going to have a solid in the bottom of my reaction at the end. Okay, I'm going to have some kind of salt, right, because it's a metal and a nonmetal, that precipitates out, it falls out of solution. Now, there is a name for these reactions that we didn't learn last year that we're going to see in AP, and it's called a metathesis reaction or an exchange reaction. So double displacement reactions, acid-base reactions, which fall into that, can also be called metathesis reactions. And the reason for that is it appears that the ions are transposing, right? They're switching places, right? So you can see in this bold print here, I have silver and I have chlorine. And these two things have come together to make AgCl. And the non-bold species have come together to form another. And this is absolutely a double displacement reaction. It just has another name, a better name, a more accurate name, metathesis, right? When you look at a metathesis reaction, we want to balance all our ions, right? We want to write the formulas for the products, cation from one reactant, anion from the other. It's the exact same rules as we did last year with the double displacement reactions, predicting reactions. The next thing we want to do is check our solubility rules, right? So if we have a product that's insoluble, we write a little S. We say, hey, this is solid. It's not aqueous. And that tells us, hey, there's going to be a precipitation. The last thing we want to do is balance it, right? So this is hopefully a review of what we did last year with just a little extra detail, right? So a couple ways you can look at a metathesis reaction. The molecular equation is what we did last year. All you did was predict the products and move on. We're going to build on that by looking at what's called the complete ionic equation, where we break it all apart into ions, and then the net ionic equation. So this would be a molecular equation. It shows the molecules, right? The, no charges, everything's neutral, everything's balanced, all that good stuff. It doesn't show anything about the ionic nature of our compound. This is the complete ionic equation for that reaction. So here's what we're going to do. All right, we know silver is always +1. Nitrate is -1. Potassium's +1. Chlorine's -1. And when they come together, they make silver, which is still +1. Chlorine, which is -1. Potassium, which is +1. And nitrate, which is -1. That is the complete ionic equation. You can see it right there. Now, we do need to add the aqueous nature of what we're looking at. Oh, and I made a mistake because I was getting ahead of myself. If something is a solid, then when we write the complete ionic compound or the complete ionic equation, you don't break it apart because it's not broken apart in solution. So I totally made a mistake there. My bad. So it would just stay AgCl, solid. But we still have our aqueous here, so that's aqueous and that's aqueous. All right, and that's what this slide is showing. And notice that you don't break it apart if it's the solid. All right. Now, something that you might see, let me switch pen color here, and hopefully this sticks out to you, is that nitrate on both sides of the reaction does not change. It's NO3 minus aqueous on both sides. Same thing is true for potassium. Does not change. However, silver goes from silver +1 to silver as part of a solid compound. It changes. Same thing is true of chlorine. So these guys that don't change, right, are called spectator ions. And we can actually ignore them in order to write something called the net ionic equation. So we break out our spectator ions, we cross them out, and whatever remains is our net ionic equation. So our net ionic equation in this case would be Ag +1 aqueous, silver, plus chlorine -1 aqueous yields AgCl as a solid. And that would be my net ionic equation. And net ionic equations are really useful things, okay? So, excuse me. Anytime we have a metathesis reaction, we can go through, eliminate our spectator ions and write our net ionic equation in order to just look at the thing that's really changing, the thing that we really care about. That's especially true if we're after a precipitant. Let's just look at the precipitant, okay? Now, when you write your net ionic equation, balance the molecular equation first, break apart all your strong electrolytes, just like I did, cross out anything that's a spectator ion, and then whatever's left is your net ionic equation. You write it down. All right, so I'm going to make a second video starting with acids. All right, so let me jump out of here. All right, just to kind of break things up for you. So if you have questions, shoot me an email. All right, take a break. Make sure that you are working on notes as you go, that kind of thing. And again, take a break if you need one. All right, you don't have to sit down and watch all of the videos on the same day. Okay, so break them apart. All right, so if you have questions, let me know.